Hello, my name is Bunyod Abdusaidov, and my team members are Joshua, Mohammed, and Eric. And this class is CS455 Software Quality Assurance. And our topic for the final project and the presentation is detecting concurrency bugs. Starting with the introduction, what are the concurrency bugs? When many threads access shared resources in an unanticipated way, it is known as a concurrency problem. Series of facts like crashes, inaccurate results, or security flaws may come from these defects. Due to concurrent execution's non-deterministic nature, finding concurrency problems can be difficult. And due to their potential to conceal concurrency-related mistakes, traditional testing techniques may not be useful in finding concurrency bugs. Continuing to use the program or application with these concurrency flaws can lead to poorer software overall due to consistent problems left in each version, and bugs from older versions would coexist with the newer ones introduced once the new version is released. And finding concurrency bugs is essential for creating reliable, strong software systems. And two distinct approaches to figuring out concurrency issues are mentioned in this presentation. They are differential replay using a tool called ConBug and a model checking technique. Based on their similarities, benefits, and drawbacks, these two systems will be compared and evaluated. ConBug, a model checking techniques, both rely on examining program execution logs. Both methods rely on the gathering of trace data throughout the course of a program's execution to find concurrency issues. And their approaches of using this trace data to find concurrency problems vary, though. The differential replay methodology, which is extremely effective at finding data trace issues, is used in the ConBug method. To identify possible data traces, the approach examines the sequence of events between two program runs. The scalability of this method makes it appropriate for huge systems with intricate concurrency dynamics. The model checking technique, on the other hand, is more flexible and can catch a larger variety of concurrency issues outside data traces. With this approach, a formal model of the program is made, and it is compared to a list of desired properties. Finding complex concurrency problems like deadlocks or live locks, which may be difficult to identify using their approaches, is where it excels. The model verification method needs a lot of computing power, though, and it might not scale well for big systems. And furthermore, it can be difficult to accurately formalize the program, particularly for systems with lots of concurrent behaviors. And our recommended solution combines differential replay and model testing to solve the shortcomings of each method. Our technique may recognize many concurrency problems in software systems by employing differential replay to thoroughly gather trace data and model checking to find a wide variety of concurrency flaws beyond data traces. Our method is innovative in the field of concurrent fault finding since it's efficient, scalable, and inclusive. We went into detail about the steps taken in our proposed method in the part under supporting details for the novel contribution. And this involves employing model checking to find concurrency problems and differential replay to collect trace data. We'll also talk about how to improve and hone our plan to make it more precise and effective. Concurrency issue detection in software engineering continues to be a key difficulty. We want to enhance the detection of concurrency concerns in software systems by examining two distinct approaches to identifying these problems and offering a unique strategy that combines their merits. Our approach is efficient, scalable, and extensive, and it has the potential to have a substantial impact on the future development of more dependable and long-lasting software systems. Concurrency bugs and vulnerabilities are an inconvenience in software development. They occur when bugs from previous threads are present in the following threads coming after the initial thread. This presentation will include information about the prior works on the subject, as well as the comparison of those works, our contribution to the detection of concurrency bugs with supporting evidence, and our conclusion and future works on this topic, including existing tools and software we could use to help to alleviate the problem. Now we move on to the software that can be afflicted by concurrency bugs. Any type of software that employs multiple threads, such as desktop applications, web servers, and distributed systems, is susceptible to concurrency bugs. These flaws can be divided into a number of categories, including data trace flaws, deadlock flaws, and a automaticity violation flaws. The most frequent sort of concurrency fault is a data trace bug, which occurs when two or more threads access a shared variable without the correct synchronization. When two or more threads wait for each other to release a resource, a deadlock problem results in a loop of waiting. When an operation that ought to be executed automatically isn't, this is known as an automaticity violation bug. These bugs and the prior methods of dealing with them will be discussed in greater detail, and a comparison of these previous methods is available, as well as to see the effectiveness of each method. We'll also talk about how to deal with the matter of any possible future work we can implement to handle these concurrency faults before getting to the conclusion of our research efforts. Thank you.
My name is Joshua, and I will be presenting the prior works portion of our presentation. In our report, we discussed two prior approaches to concurrency bug detection created by others, these being the neural network approach, as well as the static and dynamic approach. The neural network approach is implemented by first identifying three aspects of the code being tested. The three aspects that we need to know are the operations performed on variables that are common throughout the entire code, such as a variable that is accessed by multiple threads as the code may run. The second aspect we need to know is the sequence of these operations being performed. That way we can already ahead of time know whether or not something will happen that will make the variable inaccessible to other threads while the code is running. The third aspect we need to know are the synchronization techniques used. These simply tell us how each of the threads communicate with one another, as well as what we can expect the final product to look like. All of these aspects are then fed into a neural network that has already been learning from a large data set that has already been filled with known concurrency bugs. These bugs are ones that have already been detected and already have the three aspects previously mentioned flagged. It then goes through that and compares what the three aspects that we have for our code with the database to see if there are any matches, such as a particular operation being performed on a variable in this specific order using a certain synchronization technique created a concurrency bug at some point. This procedure is very good at detecting race problem, especially with the concurrency bugs. The second version is the static and dynamic analysis. During this, first, an abstract syntax tree is created during the static analysis. So we run the code and follow the logic. That tree is then applied during the dynamic analysis and runs concurrently in the different threads, meaning that each thread will follow the logic as they run. During the dynamic analysis portion, there are execution traces that can be used to find the location of bugs, because one can actually follow the tree and work their way back to find the initial point that the logic started creating a concurrency bug, instead of simply flagging where the bug is or what the bug is. You can actually follow back and find where it was originally created. Now, one of the upsides about using a neural network is, again, it's more useful for identifying race problems, as well as finding problems that have already been created. However, it does require that access to the database of already found problems, meaning that for code that is just starting out, as in a novel idea, code that has not been implemented in a particular way before, it might not be quite as useful. It might catch all of the problems for code that has been out for years, and the user is simply attempting to upgrade the code a little bit, update it, add an extra feature or two. But for a brand new code that is being run in a completely different way than it has before, a neural network may not be the best way to go about seeking or detecting or predicting concurrency bugs. The static and dynamic analysis approach works well for the varying types, and aside from simply detecting that there is a bug, it can actually locate where it occurs. This is a very important thing because oftentimes concurrency bugs are simply just detected after they've caused an issue, but the logic is difficult to trace back to where it originated from. However, due to the limitations of static analysis, as in we've only got one iteration running, the user may experience false positives during their run because the code may.
Well, thank you, Josh, and hello, everyone. I am Mohammed Sharfuddin Shah, and I will be talking about two sections of our research paper on concurrency bug detection. Specifically, I'll be focusing on our novel contribution and the supporting details about the contribution. So, to start with, our novel contribution focuses on the detection of the concurrency bugs, which is a critical issue in software development because locating and finding the concurrency bug exactly can be very time consuming and a challenging task. We have researched and put together methods using model checking in tandem with Promula language to help check for these problems. Our contribution is organized into headings that provides a brief overview of our suggested method, an important phase of the method, and the benefits of using it. So without further ado, let's take a look at the modeling phase. The modeling phase is the first step in our proposed method for detecting concurrency bugs. We use a formal modeling language like Promula to model the distributed system as a concurrent program. This stage is essential for ensuring that the model faithfully captures the behavior of the actual system in use, so that we know we are getting the real data in real time, and that'll make it easier for us to detect the problems in the future. And following the model stage, the model is put through a verification to look for concurrency-related flaws, such as atomicity violation bugs, data erase flows, or deadlock problems. The verification is done via an online model checker called something like SPIN. This process helps to locate and remove any potential flaws or ambiguity in the model, which later on saves time for the developers, the testers, and at the end for the end user, the client. Now let's talk about the benefits of using this model. Our suggested method for concurrent issue detection has several benefits over the existing ones. To start with, it can test large-scale distributed systems, which are often challenging to test using traditional testing methods. The size and the complexity of a system greatly contributes to the challenge when we are approaching with the traditional testing methods. Second on the list of benefits is that it can manage complex concurrency patterns that are hard to locate, analyze, and resolve with conventional approaches, such those in distributed consensus algorithms. Last but not least, our approach can provide precise error localization, which is very crucial when we're working with large-scale systems. This makes it easier for engineers to identify and swiftly address the issue's root cause. Otherwise, it would take hours of hard work just to locate the root of the cause. Ignoring concurrency bugs can lead to frustration among developers, testers, and end clients. Hence, our research provides an approach for bettering concurrency bug detection. We discuss how we can use ConBug and model checking for discovering these issues, the advantages and the limitations of using them, and the specifics of how to put this strategy into practice. To wrap up, our proposed method is a viable option for detecting concurrency bugs, and it's worth taking the time to attempt to implement it. It is a comprehensive and effective approach that can help detect and resolve concurrency.
Hello, you all. My name is Eric Morgan, and I'll be covering the conclusion of our presentation over detecting concurrency bugs in software. And so, on this slide, we're starting to near our conclusion. We're covering the analysis of recent approaches to concurrency detection. So, concurrency threats are becoming more prevalent, and they're also becoming more difficult to deal with. This can cause problems like crashing and frustration from developers and clients alike. It's really not fun to deal with. We'll be analyzing two papers for our solution. ConBug, Detecting Concurrency Bugs Through Differential Replay by Wang et al., and A Model Checking Approach for Detecting Concurrency by Yang et al. To help find our solution to this issue. So, our solution includes the use of the ConBug tool and differential replay. Now I'll be moving on to the advantages and limitations of these methods. So So we have the advantages/limitations of using Conbug. And this is from the Conbug article by Wong et al. From the year 2014. So, getting to our advantages, it is good for conventional testing. Some of the benefits come from differential replay, which is another method we can use to help with finding concurrency issues. According to the authors, this approach is scalable. This means they can deal with a large workload. And now we're going to be moving on to the limitations of using Conbug. So, Conbug is restricted to spotting these bugs through data races, or this is what happens when multiple resource usages occur over a single thread, which is where these concurrency issues can be detected. So, when using this approach, the code will need to be instrumented, which means that extra measures will need to be added to the code to help find these errors. But whenever we do this, when we add these extra measures, the performance can tank, causing issues. So that's another limitation to using it. And now we have the limitations of model checking. And this is from the paper Model Checking that I covered earlier from Yang et al. From the year 2016. So it's not very scalable. So it can find issues like deadlocks and live locks, but isn't very scalable for complex systems. It can't get too big. Due to this, unfortunately, model checking can only help if these problems are found in distributed systems like mobile and web platforms. It can identify many of these issues, but it is taxing on the system too. It's another problem with it. And for future work, this is everything that we've wanted to put together to help find our solution for detecting these concurrency bugs. So it involves a combination approach, two things. It involves combining differential replay, the method I mentioned earlier, to check for data races, and model verification to help with the discovery of concurrency bugs, which is something else that we wanted to add to it. So continuing on our future work, we have the implementation of this, or how do we practice this? So we combine both of these strategies, differential replay and model checking on several systems, along with, so not both, but we're actually using model checking, model verification, and differential replay, all working together on several systems. This combination approach will help because of the combined advantages of both methods, and it can lead to more reliable software in the future with less of these concurrency bugs being detected, which hopefully, just because they're undetected, hopefully means they're gone and not just hidden from us. And so we need to optimize this, get to optimization. This is needed to be less taxing on our systems and increase efficiency and precision. So we'll need to be involving the system trace, and the observable system behavior will be required. And for those who are interested in machine learning, artificial intelligence, and all that, this will be involved as well in the process. This will help with identifying and finding these concurrent bugs. And so we get to our conclusion. By putting our method into practice, companies will be able to reduce the amount of concurrency issues they have to deal with. While it may be effective, it isn't without flaws, as teams may still deal with performance hits and bugs being hidden behind more elusive triggers. This is what happens when we combine these approaches. It can cause both problems with those approaches to come together, and it can sometimes be a headache on both sides. But by implementing these methods, we can overall reduce the amount of these detectable concurrency bugs. So, as we reach the end of our presentation, I'd like to thank you for your time and attention.